Go ahead.
All right. So hi, my name is Colin Dixon. I'm a contributor to OpenDaylight, and I don't know, I guess that's probably about many other random things I could say to describe me, but I'll just stick with that. I'm also a principal engineer at Brocade. Welcome to the first OpenDaylight SDN meetup in Austin. I have some slides ready, but yell at me if you want to have questions, anything like that. It's not designed to be a railroad. It's just designed to sort of be a help me walk through things. And so really I wanted to try and walk through a couple of different topics, and we'll see how many of these we get through and whether people are interested in them, and I might fly through some of them and we can spend more time on others. But I wanted to do a really quick what is SDN, then a little bit deeper into what is OpenDaylight with that in context, go into some things that I've learned personally, sort of getting involved in open source and OpenDaylight in particular, a little bit about what OpenDaylight has done so far in terms of its metrics, where OpenDaylight is going if people are interested, and sort of my own personal take is sort of some grand challenges in SDN, things that we don't have answers to, but we're trying to figure out, and sort of interest me. So that's that's sort of what I'm hoping to cover, and we'll get through some of this or not, or whatever people are interested in, just let me know. And I got this. Anyway, so traditional networking has sort of worked. You have a bunch of different boxes. I'm just gonna call them switches. Sometimes they're routers, sometimes they're hubs. I'm gonna call them switches for everything. And they basically connect to each other by wires. Right? That's the dead simple. It's literally boxes and wires. That's it. And traditionally, each individual box is its own what's called a data plane, which just forwards packets back and forth between the different places. And in order to basically figure out how to do that, each box ran its own control plane on top of it. And the control plane is the smarts of the box, who sort of figures out what they should be doing, and they tell the data plane how to do that. And so this is sort of, think about it as brains, and the control plane is the brain, the data plane is sort of the arms and limbs that are going to actually go out and do the things you want to do. And this has sort of been how traditional networking has worked. And so the data plane is really, really, really fast. It does really simple things like match action. It basically says, this packet, the destination is 5. Everything with a destination of 5 goes out this port, and that's all they do. The control plane, on the other hand, is slower and does sort of more complicated things, like it asks, hey, who is the other end of this wire? Okay, they said their name was this. I'm going to build, and then basically I'll tell them my name, and we'll actually propagate that information throughout the network. We'll build up a view of the network, and we'll try and do routing on that. And it's really actually a full general purpose processor that runs code. And so sort of networking hardware started off actually as all on this side, which is it was all done with sort of general purpose code. Like literally there was a C program that said like, if the 5th offset into the packet is a 0, send it this way. And as it needed to get faster, we sort of baked more and more stuff into hardware. And sort of this dichotomy is, the observation of SDN is that this has what's evolved inside of all the boxes that run networks, which is that you have big sort of complicated general purpose programs that run on an embedded processor, but a fully general processor that sort of do the big sort of scale of 10 seconds kinds of things in your network. And you have very, 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 very fast hardware that is very inflexible, that does sort of the brute work of moving packets around the network. And so you can think of your data plane as a cheetah, and your control plane as something a little bit slower. And occasionally something a little bit meaner. The data plane is usually so simple it can't do something wrong. The control plane occasionally will put your network in a kind of a nasty state because this is general purpose software. Software-defined networking is really, at its core, about taking these per switch control planes and saying, these are software anyway, they're general purpose code anyway. Let's drag them out of the individual boxes, put them all in one place, logically centralized, and have that basically communicate to the individual data planes. So there's one control plane for your whole network that makes the decisions. And then basically you run this whole thing on a commodity x86 server as opposed to on specialized hardware. And this is where it's sort of software defined. It's always been software defined. This is just saying, I'd like to make it actual software that humans can write, understand, deploy, redeploy, and use that then controls your network. So the result is, rather than having sort of the individual boxes make the decisions of how the packets go, you have some piece of code that you write, and this is sort of what OpenDaylight is one of these centralized control planes for SDN. And the idea is that when you do this, you get really cool things drop out, which is that it's not just people at Cisco or Brocade or Juniper that can modify the boxes which they ship you, it's that you have an open API to go control the way they work. And so the result is you can ship new features, new ideas, and new stuff out into your network very quickly. And so this is sort of, in a nutshell, the difference between SDN and traditional networking. So anyway, if anybody has any questions.
Quick question.
Sure.
I'm new to this. I'm just curious. So you extracted it from each one of the ones and you put them in over here.
Yeah.
How does that affect the speed that it gets to that? I mean, it was, I guess it was right on it before, but now it's
so the answer is it does. Although these two things were operating at such different timescales already, that the difference is, so like the ASICs, for instance, like a 10 gig switching ASIC, a packet takes about a microsecond to transmit on the wire, which means the ASIC has to be able to handle a packet per microsecond per port. So a 64 port 10 gigabit per second switch is handling 64 packets every microsecond, whereas the control plane is probably handling things like once a millisecond. And so there's already a 3 order of magnitude gap between the processing time of the local CPU on the switch and the switching ASIC, the actual hardware chip that was doing it. And so this is making that maybe 10 milliseconds, but going from 3 to 4 orders of magnitude is just not the end of the world. The actual bigger problem is what happens if there's what happens if these lose connectivity to each other.
That's another issue.
Yeah, and so that's actually, the latency doesn't kill you. You can get the latency lower. 10 milliseconds, part of the reason why the latency is so bad is just because nothing was ever meant to be updated this fast remotely. And so actually the stack running, because there still is a control plane here, it's just the control plane is changing to being a very, very thin shim that just translates this message down into the switching chip itself. Because there still is a processor here, it still is the thing which receives the commands. The actual issue is, and so the latency actually is tolerable. It's 5 milliseconds, something that's well engineered. And the real problem is what happens when they get disconnected. And then what do you do? And traditionally, like something gets disconnected, it's fine because it's not critical infrastructure. You just sort of let it fail for a while. But when it's your network, it gets more complicated. So that's actually one of the grand challenges at the end is sort of how do you resolve this conflict, which is that you really do want to be centralized and separated because that makes it easier to understand, easier to think about, easier to manage. But when you centralize, it needs to be physically distributed to be fault tolerant. And so how do you get something which is physically distributed and logically centralized and make it actually behave the right way, which it turns out is even harder in networking than it is for people in like data centers where they've solved this problem in different ways. So just to illustrate this and this should help sort of understand some of this, so this is a single switch. It has its switch chip, which is the really fast ASIC here, has the control plane CPU here, which is running the CPU, and these are basically ports and the links that are coming out of it. And so if a packet comes in, and this is just think of these as addresses, so 0A is one host and 0E is a different computer. And so if this packet comes in, traditionally what happens is it goes through and basically it does a lookup in the table. So this packet went through and said, if the destination is 0E, send it out port 5. So this is 1, 2, 3, 4, 5. But at the same time, the packet, because it gets sent out to the control plane where the source is 0A, which it hasn't seen before, it knows the packet came from this port because that's where it came in. And so it programs into its sort of forwarding table, hey, if you see anything for 0A in the future, send it out port 1 because that's where I saw that packet come from. I'm going to assume it came from there, that's where that guy lives. So that's sort of how traditionally this works. It all stays inside the box figures out what it needs to know about the world, and it just keeps working. In SDN, you introduce a controller which sort of sits outside, and this control plane CPU, sort of the control program gets smaller, and basically in the limit becomes just a translator between, basically an external control plane, which is the SDN controller, and the switch chip, and basically the switch chip itself. And most of the features, or interesting or complicated features, drift out into sort of this more maintainable, a little bit easier to change controller. And so instead, if a packet came in at this point, it's a packet from A to C, it comes in and basically gets here, and there's no rule to forward it. So it says there's a table miss, basically. There's nothing here. And on misses, it sends it to the controller. So it goes up to the control plane CPU and out, and that sends it to the controller. The controller, once it has that, basically, it's going to have, it has knowledge of all the different switches in the network. If this address exists somewhere in the network, it knows where to send it. And so it actually is going to look up, hey, I know that C is at port 3, and so I'm going to forward that back down. I actually install a rule on the switch that explicitly says, hey, if you ever see anything with the address C, send it out port 3. And then actually send the packet that it received back out into the network where it can be forwarded and sent to the right place. So this is the fundamental difference between sort of SDN and traditional networks, sort of at the device level, and how packets go through. So hopefully that at least this makes some sense, I hope. Anybody have any questions?
No, with the SDN, it's still populating the tables, right? Or not?
Who?
The SDN is still populating the...
So yeah, so fundamentally what happens in the data plane hasn't changed at all, which is the data plane has a bunch of, it turns out, do we have markers in here? It turns out that like the way switches are built is that they have a bunch of tables. And basically when a packet comes in, it goes through a series of these tables. And each table says, hey, I'm going to look at the following bits in the packet, and I'm going to say either drop it or forward to the next table or send it out this port. And so that's sort of fixed because that's what Broadcom and other companies ship, billions of a year. And that's cheap because that's the functionality everybody wants. You can't change that. What you can change is sort of how that gets populated. That's what's still done on general purpose hardware, which is you can replace as you see fit. So the answer is, yeah, the tables stay the same. It's just how the tables get populated.
Okay.
That changes. So basically, who's programming the tables? And actually, even that doesn't really change. It's just that where the intelligence of what gets populated changes, which is like, it's still actually going to go from the SDN controller to the control plane CPU to the switch chip. It's just how much processing happens in which place and under what circumstances.
So is there zero logic in the control plane CPU? That's just an interpreter from the controller, the SDN controller to the chip?
So in reality, what happens is they're basically most switches that support. So OpenFlow is the canonical protocol that's used. Most switches that support OpenFlow have two modes. They have sort of an OpenFlow mode and a normal switch mode. And basically, if you put them in OpenFlow mode, what it says is load almost nothing that would normally go in your control plane. Instead, just load this little program that translates OpenFlow messages to table entries. And then if you sort of open it in normal mode, it loads up all of its normal software just the normal way it would run every day. And so that's one of the reasons why this sort of SDN is interesting, is because by and large, the switch you have in your office, in theory, should be able to do all of this stuff with just a firmware update, which is like you just install new firmware on it, and that should give you a mode where you could have it act like this instead, since it's basically just disabling functionality, not adding new functionality, if that makes sense.
Yeah.
So,
But where are the forwarding tables actually?
they're in the switch chip, they're in the ASIC.
On the switch chip, okay.
So that's where and there's like a table for Ethernet forwarding, IP forwarding, there's tables for multicast lookup, there's tables for VLAN modification, there's I have a slide, which I'm not legally allowed to put up here, which shows all the tables in a Broadcom ASIC, but without making you guys sign an NDA, I can't put it on the slide,
Okay.
for reasons which are mind-blowingly Actually, I wonder if I can get the OFDPA, maybe I'll look that up in a second. There are some public documentation, but there's like 30 tables, and there's basically a graph through those tables, this pipeline that it follows, where it sort of goes table 1, and then you go to one of tables 3, 4, 5, or 7, and then those tables can go a different place, and you end up with sort of a logical pipeline as to how packets flow through it. And those tables are all located in super, super high speed SRAM and TCAM in the chip. And so SRAM is used for sort of hash table lookups, so like the destination MAC address is 5. Here's lookup. And TCAM is ternary content addressable memory, which is used for things where I might not care. So that's where you type a subnet mask into your computer, it's like 192.168.something.something. This would basically say, hey, I want the first things to be 192.168, but I don't care about the next two. And that kind of memory is more expensive because don't care is harder to represent than yet 1 or 0. And so that kind of memory is basically where actually some of the really cool stuff happens, where you can say basically, I want packets that have the following first 17 bits of their MAC address, and then I don't care about the bits after that. And that stuff is all sort of stored in here, along with a very, 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 very small amount of buffer that's very fast for storing packets while they're waiting to be transmitted. I think something like, 9 megabytes of buffer. So like ridiculously small because it needs to be incredibly fast.
Okay, if we go there, since you were talking about the table arrangement inside the, so you're talking from the hardware ASIC perspective, so I come from OpenSH background.
Yeah.
So there the concept of table is like, you can put anything in it.
So so that's of course one of the first things that people did with this was to realize, hey, it's taking us kind of a while to get the hardware vendors to do this stuff and do it in a way that makes sense. Which is to say, I think the first switches that actually do this in a way that makes sense, that came onto with the software that runs on them, came out about 4 months ago. I mean, like that's how, and then this has been happening, so that's like 5 years or 4 years after OpenFlow came out, all this stuff. So in the meantime, people ended up building software switches, and that's really useful for you have like a hypervisor and you have VMs running on it, and the switch which connects all your VMs to the network and VMs to each other. It's running in software, so there's as many tables as you want, with as many features as you want. And this stuff all gets a lot less relevant. And actually, the Gartner hype cycle for hardware-based SDN is right now at sort of the bottom end of the trowel. Which is that there was all this hype and then nothing happened, and now just as we're actually getting the real stuff that works, people have basically given up. And it's all about software. And so the software place, you have as many tables as you want, they do as many things as they want, but still actually the ability to go out and remotely program the tables and say, here's how they work and here's how it should go through, is incredibly valuable even if they're completely configurable. Because you need some open API to go configure them.
You're probably going to get to this later, but you were talking about fault tolerance being tricky, and I guess if the hardware hasn't changed, can't you just revert back to traditional networking mode, or is it detection that's the problem?
The issue is just, so it used to be that you had, the problem is essentially all of the protocols that you would have used to have the different switches. So if you move back to, let me pull this slide up really quickly, because this is useful.
Sorry.
So all of the protocols that we're running, so basically what's happening is that there's like logic running here, and it's making assumptions about the logic which is running here in order to function, and also about the logic which is running here. Basically, they're running routing protocols, things like, there's a thing called like OSPF, ISIS, or BGP, and they actually are expecting each other to speak the same protocol. And when instead I set things up like this, I no longer have them run that protocol anymore. And so either I would have to run that protocol here in order to interoperate with somebody that wasn't doing the same thing, which you could do, and that might work, or there's nothing running here at all. So this guy, when he tried to put his control plane back up and do stuff, would find that nobody was willing to talk to him because they weren't even speaking the same language.
Okay.
It's sort of like, roughly speaking, it's like in this case everybody is speaking French, and in this case everybody is speaking German, and so if this guy flips to French, he's not going to have a very good day in terms of getting stuff done. Like, it's just not going to work, if that makes sense.
But can you turn off the control plane completely in each of the routers?
You don't turn it off, you just tell it to not do anything unless the controller tells it to.
Okay, so if you want to install SDN on top of the traditional routers, you have to do something to the traditional routers that...
Yeah, you install new firmware on them, basically.
Okay, you still have to do something.
Yeah, and then like Brocade, for instance, ships switches. I think we're one of the few people that work in completely hybrid mode, which is to say that you can basically say, like, I install 2 complete copies of the firmware on the switch, one of them that handles things the normal way and one of them that handles things the SDN way, and then you need rules that basically determine which different control plane each packet hits. So some people do it by ports, which is the traditional way, which is the ports 1 through 7 are SDN and ports 8 through 9 are normal.
I see.
And that's really frustrating because that means your traffic can never cross between the two of them. And so instead, some people do it with VLANs. They say like VLAN 7 is SDN and VLAN 12 is a normal network, but that still doesn't quite solve the problem. And so
there's also the you have a perfectly good network, you just wish it were a tiny bit different approach, which is
Yeah.
let the stupid switch do its job, and then
And so
Program the things that do slightly different things the way you want them to.
And yeah, the other way is to say, let the switches do their normal stuff. Everything gets normal except for the fact that basically SDN can reach in like sort of the hand of God and say, I know that you decided this rule should look this way, but I'm telling you different. It should go this other way. And so you can basically cherry pick the few things you want to have it differently in your network. And that's been the way, actually, it's been Cisco's approach to a lot of this. And
We're not the only ones.
What?
We're not the only ones.
Fair enough. So the key advantages of this sort of are, it enables a little bit faster innovation because you're developing software as a third party based on x86 software and languages people know, as opposed to writing embedded C for a processor that nobody has access to. It has to then be signed by a key that only the manufacturer has, or else the router won't boot the software. You also sort of get a global view of the network because you see all the switches in the network. So normally switches have to make local decisions based on just what they can see around them. And so right, if a link goes down, they have to sort of make a local decision as to how they're going to reroute traffic around that link. And if you had a global view, you would be able to say, oh, here's the other path you should be using, and you can get faster conversions that way. You can also do things like security enforcement based on knowing both endpoints of the communication. So as opposed to switches, normally you only get to see one half of things, right? You're either at the entry point or the exit point. You can't see both at the same time. Whereas the SDN controller can actually say, hey, a packet came in at point A, destined to point B. I know stuff about both of those points, and I can make decisions about it with all of that information. In theory, you also get simpler switches, although in practice that turns out to not be true. You can also potentially do stuff where you can now drag in virtual compute, virtual storage, and networking, which if I was still employed by IBM, I would call software-defined environments. But if I'm not, since I'm no longer employed by IBM, is OpenStack, which is basically how do you drag all this stuff together? Because now I'm controlling the networking, where the virtual machines are placed in the network, where storage is attached, all in software, sort of in configurable ways, so I can actually do them simultaneously, which ends up with some really cool things. The drawbacks, as I mentioned too, is that like centralizing things that used to be dead centralized, oftentimes with some people crying about scalability. I think that's, I disagree with that statement, but that's a whole argument that we can have on another day. Does SDN scale would be a great topic for a future meetup.
It kind of depends on how you do it.
That's not really fun. I mean, somebody has to take pro and somebody has to take against. You have to have them fight to the death.
I refuse to be pulled into your binary view of the universe.
So there's a potential bottleneck, there's a potential single point of failure, which is sort of this fault tolerance stuff, and then there's also sort of interoperability issues, which is by pulling everything up, I basically, one of the reasons why I made it faster to roll out new features is that I have control over everything, so I can ignore all of the interoperability and standardized protocols and all that stuff. And so the result is because I'm controlling everything, I can ignore them, but when I ignore them, then now I have to interoperate with the rest of the world, and I don't do what they're used to. And so this is actually a big area of sort of people focusing. The really high level view as to why people are actually doing this is because essentially it used to be we had these things, and this is another thing where I'm not working for IBM. We used to have these big computers that took up whole rooms. We still do actually. IBM still makes most of their money there. But they had specialized hardware, specialized operating systems, specialized applications, and we basically eventually figured out this was a bad idea. And we created, an open interface for the microprocessor, basically x86. We created a bunch of different operating systems with standard interfaces, and we wrote apps for them. And the result is we went from vertically integrated, closed, proprietary, slow innovation with a very small industry to basically the whole PC industry we have today. And this is the same thing as basically what's happening with SDN, which is that networking has traditionally, and again, I'll say this, still a lot of networking is going to happen this way for some time to come, specialized hardware, specialized control plane, specialized features, and moving towards having sort of basically people that make white box switches or commodity switches that you can buy for essentially the cost of the unit with open interfaces, then open control planes run on top of that, one of which might be OpenDaylight, and then you can actually write applications on top of these as well. And there's probably going to, and so this is the same thing, vertically integrated, closed, proprietary with slow innovation, moving towards sort of horizontally integrated, open interfaces with rapid innovation kind of model in networking. And OpenDaylight is one of these things which is enabling it, and if I had my way, it would be only OpenDaylight, but that's probably not true. And in fact, most ecosystems seem to survive with 2 or 3 things at each level. That's sort of the way they work. You have Linux, you have Mac OS, you have Windows, you have Android, you have iOS, you have sort of a couple of these things is tolerable. Infinity of these things is really bad for industries in terms of innovation. So that's sort of what SDN is fundamentally and what's different about it. And at sort of a 10,000 foot level, OpenDaylight is one of these control planes. That's sort of what I know the most about. So I was going to dive into what OpenDaylight is next, but I wanted to stop and see if there were any questions or things people wanted to ask before I dove into OpenDaylight. Or tell me to slow way down.
You mentioned x86 a lot. That's the chip, right?
x86 is, yeah.
The Intel-based stuff.
So x86 is the Intel architecture's instruction set for general purpose computer processors. So like the processor inside my Mac is an x86 based Intel chip. And that's to differentiate it from...
Do you deal with like PowerPC chips and other chips? Or?
I say x86 just as a stand-in for generic commodity CPU that you could go buy at Fry's.
You could just as well do it with an ARM.
Yeah, like ARM, Power, Spark.
That reminds me. I need to see with Carafe if I can get us onto a Raspberry Pi.
Yeah, so we run Java for everything that we do. So basically, if there's a JVM for whatever hardware you have, OpenDaylight will run on it.
Oh, okay.
So there's nothing. You just use it as a stand-in for generic chip that you can run things on. That is dirt cheap and all the nice properties that we like. That sort of as to contrast it with like it's as to contrast it with like a Broadcom Trident switching chip, which doesn't run general purpose code, it just does table lookups very, very quickly. Or to contrast it with, and so let's say, or to contrast it with, so something expensive, like, I don't know, a supercomputer or something. I should say it's generic and general purpose, that's all I mean.
So just a question on the SDN adoption. It looks like the CapEx is going to be huge, somebody who wants to adopt it in their data center infrastructure. If they want to replace their existing network infrastructure with the OpenFlow enabled switches, the CapEx is going to be huge. How is the industry receiving that?
Badly. No, so there's a bunch of ways. So there's a bunch of ways to answer that. So sort of SDN promises both capital expenditure savings and sort of operational expenditures. But so the capex of adopting SDN is largely artificially created, which is to say that there's nothing to stop switches that you have today from running firmware that would enable them to run something like OpenFlow and be able to actually have a controller program them. Except for the fact that the people that release the switches aren't shipping the firmware. And in some cases, actually, you can root your switch the same way that you would root your iPhone, and you jailbreak it and you can install custom firmware on it that would run OpenFlow just fine. Because essentially, most switches are the same at the bottom. Almost all switches in a data center today run a Broadcom, some version of a Broadcom Trident ASIC at the bottom, or a Triumph, which is the 1 gig. Trident is 10 gig, Triumph is 1 gig, those are the code names. So they're almost all the same in terms of the hardware that actually moves the packets. There's just this weird thing in between the controller and that, which sort of won't get out of the way, which is the firmware that your vendor ships you. And vendors will tell you, well, this firmware is giving you lots of features you like, and they're right. It probably is giving you lots of features that you like, but also you could swap that out and install sort of generic firmwares. And there's an open source project called Indigo, which basically is one sort of attempt at it's basically OpenWRT. Does anybody ever play around with this? There's
Linksys used to support it in its...
Yeah, there was a router called WRT54G. And the WRT54G is like this blue box with two antennas. Like when you think of a wireless router and you have like this blue box, this is Linksys on the front, it's got these two pointy antennas that you can rotate around. It sold like 50 million of them in like a year period. It was the most popular thing, and people figured out they had to put Linux on it, and they made an OpenWRT version of Linux.
Well, people figured out there was Linux on it.
Yeah, the people figured out there was already Linux. They sort of reverse engineered what was being done, and they put a version which you could then flash onto your device for you. And so if you were really, really crafty, people did this. I ran it for a while at home, and sort of it worked pretty well most of the time, but it was missing certain really useful features, like a web user interface for a while, and then somebody wrote one of those. And so the same thing is happening with sort of with hardware, which is that people are releasing sort of custom third-party firmwares that you can install. And in one case, actually, Broadcom is releasing their own. So Broadcom makes the chip at the bottom, released their own thing called OpenFlow Data Plane Abstraction, which is not a firmware in and of itself, but it's sort of the bare bones skeleton you would need to build a firmware for any of a large number of their chips that would support OpenFlow. And so if you have access, actually, if you can log into the Linux process that is running on your switch, you can install OFDPA and you can run it. And it's actually shipped and like attested to by Broadcom, who makes the chip at the bottom end, so it uses their drivers to get to it and all that good stuff. So in theory, CapEx shouldn't be a problem. In practice, it's painful. And so adoption has mostly been add software at the edge. But I can go deeply, and I can answer any, basically, I can talk forever on almost any of these topics and interact with people, so yeah, right now, CapEx is a problem. The result is most of the adoption has been products like VMware's NSX, which runs purely at the edge. It's basically, it sits in the software vSwitches that sit underneath the virtual machines. And so packets come out of virtual machines, they hit the vSwitch does things to them, and then it just assumes the network is going to work and forward IP traffic correctly. So it does everything sort of in a layer in between the VM and the network itself. And that's where SDN has been most deployed. My guess is that's going to shift over the course of the next 3-4 years, because there's just a lot of advantages to being able to actually control the physical network. And if you do this, among other things, you now have to manage 2 networks. Now you have to manage all of your VMs, your VM network interface, and then your network, all 3 independently, as opposed to you had just 2 before. And some of that gets easier because you've factored it into 3 problems, but some of it gets harder. Anyway, so are there any other questions before I? Okay, so what is OpenDaylight? I dragged this language, I think, directly from the OpenDaylight website. So OpenDaylight is an open source software project under the Linux Foundation with the goal of furthering the adoption and innovation of software-defined networking through the creation of a common industry-supported platform. And we have 3 goals, one around code, one around acceptance, one around the community. For code, we want to write code and ship code.
Code is the good in the realm.
and get code in people's hands. And basically we have a very broad view of what kind of code we're allowed. Basically, I think Ed is famous for saying like he's pretty sure that a 3D rendering engine is probably not going to be something we ship inside OpenDaylight.
It's actually currently explicitly forbidden by our board, but yes.
But beyond that, pretty much anything you can imagine that would support us in getting SDN stuff done, we're willing to build. And so we have all kinds of projects around, from everything from sort of enhancing existing network simulators to building, core control plane stuff to basically anything you can imagine. We're willing to basically go take it and try and incubate the code and get it to work. Acceptance, basically we want both people to use it directly, which is the users to use it and vendors to use it. Where basically it was created by like people like Cisco, IBM, HP, Brocade, lots of other companies, and so sort of they created it in part because they want to use it in their solutions. They want it to be the Linux of networking, where they'll pull it off the shelf. It'll do most of the stuff that's easy for them. They won't have to re-implement all of that stuff. But there's also, as a foundation, they want to be able to have the core thing actually be usable by humans as opposed to just companies. We're getting there. I mean, if you're reasonably competent with Java, you can probably get it down and use it to do something useful by yourself. But really, right now, to do really cool stuff with it, it's really designed kind of like it's like the Linux kernel. No normal person is going to go download the Linux kernel by itself without a distribution and try and do stuff with it. They're going to download like Ubuntu or Fedora or something. And so similarly, OpenDaylight right now is mostly consumed through like a Brocade distribution of OpenDaylight, a Cisco distribution of OpenDaylight, or even just products that you have no idea that OpenDaylight is at the core of them. It just happens to be that's the best way to build those products. And the last thing, this is the most interesting for me, is a community, which is to have a thriving and growing technical community, contributing to the code base, using the code in commercial products, and sort of adding value around and above and below and all sorts of things. This community thing seems like the sort of hippie commune thing when you first talk about it, and you say like community is this real thing, there's a real community, people come together, they work on stuff, they solve things, and the community is a bigger thing as a whole than it was at any part. It's not all bullshit, as it turns out, despite the fact that that's what it sounds like when you're on the outside. Community really is kind of strangely powerful and really weirdly transcendental about how sort of a product goes. It's the difference between things that are really successful and things that aren't. Like the reason Linux is the base of everything that it is because there's this community of people that's constantly pushing it, evolving it, tweaking it, testing it, changing parts of it. And the fact that it happens to be done a lot by companies, some by people, doesn't really matter. It turns out sort of people have this allegiance to the community and to the thing that they're building, which produces really weird dynamics that end up being really nice for the thing that they're building. So what are we actually building, now that I started talking about that? We're basically building an SDN platform, and the goal is that sort of we want to handle as diverse use cases as we possibly can, and as many different implementation ways as you want to do it. And this has been both a huge asset and a curse. The reason why it doesn't just do something when you download it out of the box and use it, and it isn't like a product, is because we want to make it as like essentially a set of tinker toys, rather than one particular set of things that it can do. But of course so we sort of have the advantage that it's used for almost anything. The bad news is that out of the box it doesn't do any one thing amazingly yet. We might get there. I mean, this is, and we'll see how we do. We also want to provide sort of common abstractions to deal with the network, and these are sort of northbound interfaces. Like one thing is like, we build a topology of the network. So you can say, hey, where are all the nodes in the network? Where are there links between them? Where are their hosts attached to the network? And that's represented in one way, no matter what's going on the bottom end. So when people want to bring in sort of a new protocol at the bottom end, or support for something else, they sort of tag into this model of the network, and they can add new things onto the topology, and the result is that, but on the top end, everybody gets sort of like, hey, I just want to know what nodes there are on the network and how they're connected to each other. And that stays the same across all the different things that happen on the bottom end. And then we also provide southbound drivers that sort of plug into that. These are examples. OpenFlow is sort of the canonical SDN protocol. I can go into that in a lot of depth if you want. This is just basically lots of different things that we can go out and talk to in the network through different mechanisms, because different devices speak different protocols, or you want to manage them at different levels. And basically, the third thing is to provide intermediation between sort of this southbound and northbound. So we really want to provide like an API to write applications, like you would for your iPhone or whatever, and then, and I guess Android would probably be a better example, but like, and then basically it doesn't matter what handset you happen to be running on, it doesn't matter what network you happen to be running on, we're going to try and support as much different stuff as we possibly can and make it easy to program, just like you would program an app for your smartphone. And then sort of in between we have sort of network services that try and use these different interfaces to do cool stuff, and applications, and sort of whatever else we need to make it work. So we have really, so it turns out actually like host tracking is something we built entirely on top of other systems. So we have one thing that sort of tracks where all the different switches are on the network, and we have a different thing that uses that information to sort of capture traffic and figure out where hosts are in the network in different places. And so that's like a service built entirely, so this is on top of sort of existing services that we sort of, so you can layer them up the same way you would layer up an operating system, where you start with like, block level access to your disk, then you have sort of, then you have a file, then you build a file system on top of that, and on top of a file system you can build applications. We're doing sort of the same thing, only we're slowly figuring out what the right services to have are. So like one of them is, hey, just tell me who you are and what you're connected to. And the next level up is, okay, give me the ability to capture some of your traffic. And the next level up is, okay, now that I've captured your traffic, I can figure out what's going on the network, where the hosts are, that kind of thing. And now once I've done that, I can feed that into basically something that's going to install the rules in the network to do, segregating the hosts in different zones. The hosts that are in zone 1, zone 2, and zone 3. If you're in the same zone, you can talk to each other. If you're not, you can't. So sort of just building up these layers, like we have an operating system today, except nobody's really done that for networks. So we're discovering what the services we need are and how they all plug together as we go along. So this is what it looks like. I guess it's like a 40,000-foot view, which is we have drivers at the bottom, which talk to devices. We have an abstraction layer in the middle, which I can go into a lot of detail, but that's sort of fine. Then we have sort of core services that run on top of that, and they explore APIs, which you can use either through Java or through REST, and you can build your applications. So you can literally write an OpenDaylight application in Python, and all it is just a REST API. So you would program it the same way that you would query Twitter for new things, except that instead of getting tweets, you're getting stuff about links and switches and the rules installed in those switches. And I'm going to skip over this because it's probably more than you want to see. This is sort of a wire diagram which just goes into a little bit more detail as to how things are set up and what you can use. I just put it up here really just because you can see sort of a bunch of the components that are there. One thing which I wanted to pull out is the base network service functions, which are things like, which are this thing here. We have things like a topology manager, which tells you basically where the devices are, how they're connected. We have statistics, which tells you sort of what flows are going on and how much they're using. We have a list of all the switches in the network, separate from how they're actually connected, but you can actually say, not about their connectivity, but just the switches themselves. You can install rules, you can track hosts, and this ARP handler is sort of just basically how do you get core routing working, and you can sort of ignore that. But this is just sort of showing, here are some of the things you can do.
Has anyone even tried to do this for Helium yet?
So this is for the high version release where we only had about 15 projects. We have 27 projects
27.
in the second release. So you can imagine this, but with twice as many boxes and thus 4 times as many lines between them or something. So it's getting,
I think it should be something very useful to do that.
yeah. So,
Very, very useful.
I saw an AD cell and MD cell there. What is the difference? I've
uh,
heard about it a lot. So I just wondered.
Okay.
we should have a second thing on how
Next week.
we get, the next meetup, or one of the other future meetups we can talk about sort of, you know,
How to
the
accept
core,
model into your heart.
the core of OpenDaylight how it works. I don't think, I mean, so essentially we have the SAL is the service abstraction layer, which is basically what mediates sort of the top level stuff which you write apps to, and so the bottom level stuff which actually does stuff in the network. And we used to have one that was based basically purely on Java interfaces. So you would say like, you know, this is, you know, basically the program of flow, there was an add flow function, it took in a switch and it gave a flow, and it said put this flow on that switch. And this was nice, except that for every one of those you had to translate that into a REST API call as well, and then you also sort of didn't get very much validation in terms of, you know, what was, whether this is a legal flow or not, and getting, and so as part of that, we've developed something called a model-driven SAL, which basically, instead of having API calls, what you actually do is you have a data model, which is, we actually have a network, the network contains switches, switches contain tables, the tables contain rules, and you can actually dynamically put data into any level of that. So something can come up from the bottom and say, hey, I'm a southbound driver, I like to add a switch here, and that switch will get added into the data model. And then from the top level, the application can basically be listening and say, hey, look, there's a new switch. And it can actually say, okay, I want to install the following rules, and it can also put data into the same data model. And so there's one sort of common, universal thing that is your whole network, and you can manipulate it or any subpart of it as you want in a common way, whether you're doing it from REST, from Java, or from Perl if somebody wanted to write the Perl bindings for it, or wherever you want to come from, you can then do and play around with it. And the interesting part is sort of, it results in there being easy to have different people from different places all modify it without having to agree on things beforehand, except for that they agree on the data model. And so before, right, if you wanted to have 2 different people advertise switches, so that there's only one switch advertising thing. There was one service that provided, hey, here are all the switches. And so you had to modify that if you wanted it to work. And now instead what you have is basically there's a data model that sits behind it, and anybody who wants to can come on and publish data into that. And we're working on actually changing it so that way, at least in your controller, you can restrict that. So there is certain access control and stuff like that. So basically, arbitrary applications can't run amok. But the general idea is that, and that's the difference between the AD cell and the MD cell. And if that made no sense, that's probably fine.
So does model-driven?
So
Can think like
in terms of
MDSR is the
capabilities-
database of the whole thing.
It's a little bit more than a database, because it's not only does it store the data tree, but it allows you to model RPCs and notifications as well. And one of the things that's highly convenient about that is when you start asking yourself questions like, what do we do in a clustered situation, right? Where I may have an OpenFlow switch that connects to node A in my controller node A, but the guy who asks for something to be done with it is sitting on node D. We can actually route that RPC call to the guy who's providing that particular information in a way that makes you not have to know about it as the application author, which is incredibly convenient. Likewise, for handling how notifications occur, there are lots of really convenient things about modeling these things. For example, when you're trying to write really performant code, you discover very quickly the data transfer objects that you want to pass between different domains. You want them to be immutable because you don't have to synchronize on them. They're never changing. The chance of a human being successfully doing that across a project of hundreds of people every time and not producing Heisenbugs is approximately 0. The chance of getting that out of code generation for your model is approximately 1, modulo testing your generation of code.
So the way I look at modeling is that it gives you sort of 3 things that are useful. One of them is it generates a lot of the boilerplate code. So like, we write a model that basically says, hey, there's a host. It has a name, it has an IP address, it has a MAC address, and it has a VLAN. And then it generates, and I press go, and it generates like a Java object, which is a host, which has a name. It has a Java interface, which is basically a set name, set IP address, get IP address, and all of these other nice things. It generates boilerplate code. At the same time, it also generates REST interfaces, so I can pass a host back and forth between between, I basically get a formatted REST interface, which will pass back JSON or XML, the host, however anybody wants to parse it. It'll actually parse that in and out for you really nicely. And then the third thing which it does is that it turns out we can do things where you can augment a model. So you just say, hey, I'm a new application, and I want to track some extra bit of information about hosts. Like I want to track the list of users who have access to that host. And so I can actually write another model which says, hey, whenever there's a host, I want you to also have a list of users attached to it. And then I can actually attach that information to the host which somebody else manages, and I can take responsibility for that subset of the model. And so you can also do extensibility sort of very nicely into those models. Those are really the three key advantages I see that I get from modeling when I do it, which is I write less Java code, I can basically get REST calls for free, and I get the ability to extend things.
Well, you also get certain other kinds of free stuff. And the REST calls for free is an awesome thing. And it's sort of the leading edge of what people are, it's the thing most people are familiar with. One of the other things that you get is, for example, we had a guy who got really excited and sat down over a weekend and wrote a JDBC driver for our data store. So now suddenly...
Which is another bit. By REST calls, I mean you get basically arbitrary interface.
You get arbitrary binding, so you could,
which is like you have a very, very small, short file. It's written in Yang in our case, which basically says, here is the kind of data that I store. And the result is that you can load that and relatively quickly build something which takes that and turns that into a schema for whatever you want to do. You can load it, you can treat it like a database, you can treat it like a REST interface for a tree, you can do sort of...
You could do AMQP bindings for messaging buses, you could do all kinds of crazy stuff.
And so it's just like, once you have sort of a standard interface, which is well documented, easy to parse, easy to understand, easy to deal with, now you can plug all sorts of things together and do very nice things. That's sort of the key advantage it has. We've had some stumbling blocks, which is getting this thing up and working and actually playing with it, getting people that they can understand it and use it has been painful. But we're most of the way there actually. I think that now it's easier to do that than it is to do just straight up Java code in a lot of cases.
Well, and honestly, I need to bring up the style guide. I freaking know what the style guide needs to look like.
So anyway.
So just one question actually. The MDSL and the ADSL, do they offer identical capabilities, one in memory, one with the rest, or do they offer completely different capabilities in terms of their API interfaces?
So there's two orthogonal questions that I'm hearing. One of them is ADSL and MDSL, what are their capabilities and how they differ? And the other one is REST and sort of local calls. Are they the same as their REST or native? Are they different? The answer is, between ADSL and MDSL, mostly depends on where you look, but at the high level, we've been trying to keep the capabilities the same or better in the MDSL, which is that we've tried to adapt everything from the old stuff onto it so that it has equivalent things. And that hasn't always been fun or easy or not brittle. So that's sort of the one side. And the ADSL, you had to hand code all your REST APIs. The result is there was this really high impedance between sort of running something natively where you had access to the real functions and REST, which is where you just got whatever the developer happened to try and expose to you. And the MDSL, which is where it is that any interface that you create sort of automatically gets pushed up to the REST calls as well. The one exception to that is that a lot of the patterns which we have in the MDSL are basically you listen for data changes. So you just say, I want to hear anytime there's a new node. And so what you actually do is you say, hey, I know where nodes sit, tell me if a new one pops up. And you can't do that easily. You essentially have to fake that through REST today, which is you can't get notified of things. And that's just a fundamental, like, what do you want to use? You use WebSockets, you use long polling.
We actually have a 3/4 implementation right now. Like, I literally, as moving the REST conf over, had to move the WebSocket port to a new port because of crap using the one we were using. So it's not completely there, but it's about 3/4 of the way there.
So the goal is to basically have REST be just like native, and that's one of the advantages you get with modeling, which is that basically because all the interfaces are well defined, you define them once, and then basically you press go and they get pushed to REST to whatever other bindings you want. And so that's what we get.
Now that we're talking at this level, maybe you can just skip to the previous slide, just
Sure.
This one, right? So I had this question when I was walking through it earlier. So we have OpenFlow 1.2 support through ADSL as well as MDSL. Is it like the entire thing is rewritten when it was being moved to MDSL?
Yes. Well, so what actually happened is that OpenFlow 1.3 and 1.0 have about as much in common with each other as like an elephant and a pear. I mean, it's not quite true.
They both evolved from unicellular organisms, goddammit.
And so the result is we were completely rewriting the plugin in order to support OpenFlow 1.3, and in the process we wrote it to work with the MDSAL instead of the ADSAL, and that's sort of how that happened. So there's no code shared between the two of them.
Okay, so the core of the 1.4 that comes through IndyCell is nothing to do with.
Yeah, we've tested the crap out of both of them. So actually, one of the few places where we actually are pretty sure that you get the same behavior in two different sets of code because we tested it really deeply. But it is technically completely different code. So, yeah, are there any other questions? And I can sort of jump around if people want to go to a different section. I can take us back to the agenda. But I mean, who is OpenDaylight? There's a bunch of companies. In actuality, it's the people that show up and actually write code. Although the companies do pay for things like this. But actually, I updated this from a previous slide I gave. Said we were running about 100 commits a week. That was only 4 months ago.
Really? Okay, I don't remember what the original slide was back in September, but
This was basically we're coming into a release, and so everything sort of we get fewer commits in between releases and more commits towards the release. But in the last 30 days, we've had 1,037 commits from 81 different people. In the last 12 months, we've had 9,000 commits from about 220 different people. So this is sort of like just an idea of how many people there are. The other thing is that we have actually, surprisingly, and this sort of always stuns me, there are people that volunteer or are volunteered to step up and do like integration, testing, even documentation in an open source community and actually do it well. By and large, and this has been really, really, really important, especially like, you have no idea how hard testing is when it is that any random schmuck can come along and change any line of code.
we're a little bit more discerning than that. But
you have no idea. It's really interesting to watch people evolve from writing code for a company where it is that they've largely been assigned responsibility for a section of code, and it's their code, they own it, and if anybody else is going to touch it, they're probably going to touch it after talking to them. To how do you write code when the assumption is that a random other person at some point in the future is going to come in, have to understand your code well enough in order to change it and fix a bug.
Well, you actually get a flip side piece of this with Agile, because Agile developers have the opposite side of the problem because they've had beaten into them that nobody owns the code, and they're assigned a thing to do, and they do their thing, and then they move on to their next thing. And there is this halfway point with open source where it's not that it's your code and nobody touches it. There are lots of people involved, but you do have a sense of responsibility towards it.
Which is to say, I mean, one of the things that we've run into is that we've had a couple of cases where people show up, basically toss a bunch of code over the wall and say, see ya, and that code dies, which is to say that like code is only valuable if the people that understand it are still there, and that code just dies. Nobody uses it, it rots, eventually gets taken out of the project, and it keeps going. So there is but it's been interesting to watch how sort of this whole thing approaches. The hydrogen simultaneous release happened in February. We're coming up on our second release, which is Helium, which is going to be in September, which is very, very soon. We shipped 15 projects, about 1 million lines of code, and we used additions. We all learned a lot of things. This basically says we shipped something. Here's what it had in it. The core controller, VTN and OpenDaylight, network virtualization stuff. Yang tools is sort of this modeling things that I was talking about. BGPLS is essentially support for a particular networking protocol. OpenFlow and the OpenFlow protocol and plugin are other things. SNMP is another networking protocol of ESDB. So a lot of it is sort of southbound protocols to support stuff, and a few companies shipping applications. Affinity, OpenDub, and VTN were sort of three sort of applications at the top end that did sort of nice things on your network.
How'd you come up with the name? I did.
I can tell that's right.
So it's OpenDaylight. So it's about so we decided to go with the stellar basically fusion elements. So the next release is going to be helium. After that, it's lithium. And after that, I'm not a physicist, so I'm going to defer to Ed and do the rest of that.
Well, actually, part of it was we held a contest for naming, which sounded like a good idea. And we were intended to vote on what the name was going to be. As it turns out, the only people who get a vote are the trademark attorneys. So hydrogen was one of the names suggested, and when things came back from the trademark guys, it was the only name on the ballot.
So I actually worked for Microsoft for a while, and when we were naming things at Microsoft, essentially there were two ways that your organization could name things at Microsoft. One of them is that you could pick a place name because those can't be trademarked, copyrighted, or anything like that. You're allowed to use them whenever. And the other way was that your business or unit could come up with like $30,000 to pay to lawyers in order to vet a name, possibly multiple times. And so it turns out elements have the same sort of property, which is like nobody can copyright them, trademark them, or do anything with them. And so that was useful.
That's good.
This was sort of what we shipped. It looks a lot like the previous diagram you saw. We have OpenStack integration, which works mostly. We use it just for L2 stuff.
5 minutes.
We have basically L2 OpenStack integration, so we can build virtual networks from OpenStack and actually support them. We're working on getting better stuff in the future, which is actual like L3 support, which is to say, right now we do it just on MAC addresses. We can't do route and IP addresses, that kind of thing. So we're relying on OpenStack itself to provide that. We'd like to shift that around. That's basically what we have in the next steps. I don't know, what do people want to hear about? So here's the agenda. I have 5 minutes because Vasu is going to tell me to stop talking. Is there anything here that people actually want to hear about? Do you want to see metrics about companies and lines of code and who shipped them and who's committed to them? Do you want to hear about what I've learned? Do you want to hear about grand challenges?
Where's OpenDaylight going?
Yeah,
All
that's
right.
what I was also
Actually, I want to know what you have learned, if that can be done.
Sure. So okay. So here are the things that I've learned, and I have shamelessly stolen many of these from Dave Meyer, who is the chair of the Technical Steering Committee. The first one is that community building is a really core objective, and in fact, like this community thing is actually probably the biggest and most potent and most powerful thing that we've gotten. If you took all 1.5 million lines of code away from me, it wouldn't hurt us for very long. And it's basically because there's a set of people that know how to interact with each other, they know what we're trying to build, we've sort of institutionally gained knowledge about how the problems are solved, what's hard, what's easy, where you should push your complexity, that kind of thing is just crazy. The second thing is that code is the coin of the realm, and this sounds stupid, but it's actually true, which is to say, that like basically people won't listen to you if you don't code. If you are actually in there in the code, like in a company, your manager tells you what to do. In OpenDaylight, if you haven't been shipping code and have signs that your hands have been on the code, nobody's gonna listen to you when you talk, because they know that you don't know what you're talking about. And it actually works. It's sort of crazy. And this last thing is sort of engineering systems are as important as artifacts, and I'm just going to stick that over here, which is basically engineering artifacts are no longer the source of sort of sustainable competitive advantage. And this is, which is to say that it's not the thing that you build that matters, it's the system which created it that matters. So it's the ability to make the next thing, and sort of that institutional knowledge that matters. And this has been true in some industries for longer than others, but this is increasingly true for software, which is to say the particular piece of software you built might be great, but it has very little value as compared to the software ecosystem that produced it and what you're going to do the next time. And so the way I like, so what you build is as important as how you build it. And my favorite stating of this has sort of been factories versus babies. So this is sort of a quote which is like, most vendors develop product like an overly anxious parent's making a baby. There's a lot of preparation and planning, and then once the baby is born, the product requires ongoing attention to reach its maximum potential. By comparison, company that I won't mention is organized itself as a product factory. Each product is the result of a unified production line, and the next product is a year or two away. Each product builds on the previous product, you ship it out, you forget about it, you produce the next one, repeat. And this is sort of the old way versus the new way of doing things. And not necessarily that either one is wrong, but just this is sort of an interesting observation, which I think is true about OpenDaylight, which is hydrogen was cool, but it's irrelevant. What actually matters is the people and the production, the ability to produce the next one that's actually interesting. And you do it even faster than a year or two in open source. And this is true in a lot of software, but networking has never really seen this happen this way before. So that's sort of what's interesting. So that's a bunch of the stuff which I learned and why transparency is really, really important. I can get into that talking to people later. Where OpenDaylight is going, let's skip through this stuff. Damn you and East and your animations.
The membership slide's actually pretty cool. I want to see that.
Which one?
The membership slide.
Oh yeah, so this is basically who joined when, and it ends in February 4th.
Didn't another very large 2-character company join after that?
Well, HP has been a member, I think.
Oh, true, but they became platinum.
They became
It's
platinum.
there.
Yeah, they became platinum.
Yeah, but they became,
So what are the
there's,
different ones? What does that mean? Platinum, gold? Just
platinum is $500,000 a year and 10 developers.
Okay, so,
Silver is, or gold is like 50 grand a year and like 3 developers, and silver is basically like, I think it's like, I don't know, $2 a jawbreaker, I don't know. I think it's like 10 grand a year and no developers.
And a documentation guy.
Yeah, and no.
Yeah, we love our doc guys. They're awesome.
Actually, if you let me trade developers for doc guys 2-to-1 right now, I would do that about 3 or 4 times. I really need doc people.
Good documentation. It's all good.
And it matters so much.
It's incredible. Yeah.
Anyway, so that's
Because we are nearing a release, that's why.
This is this is kind of out of date, but this is gonna be where it's going, which is all the black stuff is the stuff that was in hydrogen. The red stuff is the projects which have been approved since hydrogen, and there's 14 more projects in some state of preparation at the time I made this slide, and now I think some of them have been processed and others of them haven't. And this is an incomplete list, but you're adding. What we're seeing is actually a lot more. The first release was basically, hey, I'm a company, I want to ship my one thing into this. And I'm going to jam it in, and do a square peg round hole kind of thing. And sort of we're just going to barely get it to work, so that way it works sort of when nothing else is running. And so a lot of what we've seen actually, the next level is sort of, we've seen some of the same stuff, which is, we have people that want to ship just a single protocol like packet cable, which is for managing essentially cable boxes. There's actually a company right now which is managing cable boxes using OpenDaylight in the wild. It's sort of crazy.
Who?
This is the Cable Labs guys.
Cable Labs isn't a company.
They're a
giant consortium of every cable operator
Sure,
in North
okay.
America.
But they have, but I think there are people that are actually running it, but I could be wrong. But there's also stuff which is sort of how do you combine what's already there. So like we have dynamic resource reservation, which is basically trying to combine everything together to basically do things like reserve bandwidth across the whole network using everything else that's already there. And this is one of the things where it's going, which is people are writing apps that rather than trying to do their own little thing in their silo, are trying to take everything else and pull them together to do useful things across the whole network.
One of the other things you mentioned, a lot of these were just like a single company in hydrogen. In helium, most of these things in helium are actually things that involve multiple different organizations of various types, and the learning to work together process is non-trivial, but it's deeply rewarding and highly important.
So that's one of the things that is going on, which we're getting more projects that are sort of across all the different code and across companies. We're also this is sort of just like things we're trying to do, factoring apart things like the controller. This is probably not going to happen as fast as we want it to, but basically we had some big monolithic things in the first release, which we want to tease apart into different chunks, and we're doing some of that. We didn't have a data persistence, we didn't have any clustering or distributed systems, the thing was not very fast, scalable, or stable, all of which we're fixing. This is just normal, and also code quality, test coverage, bugs, adding bindings for the languages that humans like to write in. I've learned that while I love Java, many people think Java is the most horrible thing that has ever happened, which surprises me, but it is what it is. We need more code that writes code, so we have, which is basically we're realizing that you really, the less code humans write, the better off you are. Humans are really bad at writing code.
I usually like to refer to it as this, and this is why I'm a huge proponent of model-driven approaches. Let the people solve the people problems, the machine solve the machine problems. Getting, just as an example, every freaking data transfer object to be immutable is a machine problem. People are terrible at it.
Yeah.
Figuring out a tricky bit of business logic or a tricky bit of logic for how your network should operate, your machines are never going to be able to do that. That code is always going to be written by a person.
So we have a bunch of non-technical work which we're doing. So like, which is like, how do you make sure the right people find out about what's going on when they care about it? We're still sort of working at that. In general, more transparency is more better. It's sort of been my axiom around that, which is just like if you make everything open, all of the meetings are recorded, all the minutes from all the meetings are published in a known place, that goes a huge way towards making sure people find out about the right things, or at least when they do find out about it, they don't feel like it was being hidden from them. You have this problem, which is like there are enough conspiracy theories to go around that like getting things out in the open helps. It's funny that I have this on a slide from 4 months ago, but we need more people for things like release engineering and documentation. We didn't solve this problem in the 4 months since I put this up.
We considered more bribery.
And then we're also sort of like, doing things like we're moving all of the infrastructure the project runs on into rack space that we can spin up and spin down virtual machines So we're essentially like almost using the project to, which is we'd really like to be able to the things which this project embodies, which are like fast deployment, fast provisioning, fast, playing around with things, we'd like to actually use instead of what we currently have, which is there are like 4 machines in a rack, and if one of them goes down or something happens to it, nothing to replace it, and we can't get more resources when we need them. So we're doing a lot of stuff like that. But that's sort of what we're working on. And we're shipping helium. Helium comes out at the end of the month. But I think a lot of it has been, and the biggest thing.
Beginning of next month. Next month.
Next month.
Yeah. Sorry.
This month will be too early.
And that's sort of, and a lot of it is just stability, clustering, code quality, test coverage, and then there's sort of some other nice features on the side, sort of some combination of cool stuff that meshes everything we have together into nicer new form factors and actually does useful stuff. And the same old, which is like, hey, I just added a new whistle or bell off to the side. Like things like, I can now talk to cable boxes. I can now support, corner case of protocol 3 that I didn't have before, that kind of stuff. But yeah, so I'll stop there since I think I'm now 10 minutes into Vasu's 5 minutes that he allotted me.
Cool. Pretty cool.
Does this mean we can eat and socialize now?
Yes.